Hello, and welcome to the TI Precision Labs video on power supply rejection. In this video, we will discuss how changing the power supply on op-amps can introduce a power supply rejection error. We will consider both AC and DC power supply rejection. Finally, we will consider how changing the supply voltage can also introduce a common mode error. Errors from power supply rejection, common mode rejection, open loop gain, and many other types of errors can be modeled as an input offset voltage connected to the non-inverting input of the op-amp. This method of reflecting the error signal to the input simplifies the error analysis, as the error sources can be added together to find the total error. In practice, the error sources are often added as the square root sum of the squares because the errors are uncorrelated and can be represented as a Gaussian distribution. The datasheet table provides a typical and maximum DC power supply rejection, abbreviated PSRR. Later, we will look at the characteristic curves to show the AC PSRR. Note that PSRR can be given in volts per volt, microvolts per volt, or in dB. This slide shows a simulation and calculation where the power supply is reduced by 1 volt. Note that the positive and negative supplies are both shifted equally by 0.5 volts. In the next slide, we will see the implications behind making symmetrical and asymmetrical changes in the power supply. Power supply rejection in volts per volt, or microvolts per volt, is defined as the change in offset voltage versus the change in supply voltage. Power supply rejection in decibels is defined as -20 times the log of the rejection in volts per volt. The negative sign makes the decibel version of PSRR a positive number. Looking at this specific example, the simulation shows a 5 microvolt shift in offset for a 1 volt change in supply voltage. This is exactly what is expected for this example, as the specified power supply rejection is 5 microvolts per volt for this device. This slide shows the difference between a symmetric and asymmetric change in the supply voltage. The key thing to understand is that an asymmetric change in the supply voltage translates to a shift in the common mode voltage. A shift in the common mode voltage will introduce a common mode rejection error. To better understand this, first look at the default test condition shown on the far left. This circuit has symmetrical 15-volt supplies such that the average of the two supplies is 0 volts. This is the default case, and shifts in offset will occur if the power supply or common mode voltage shift from this configuration. In the second case, the supply voltage has been changed symmetrically, such that the average voltage is still 0. In both the first and second cases, the common mode voltage with respect to ground is 0, and the average power supply voltage is still 0. If either the common mode voltage with respect to ground or the average supply voltage changes, this constitutes a change in the common mode voltage. So, the second circuit does not have a change in common mode voltage because the supply is kept symmetrical, whereas the third circuit does have a change in the common mode voltage because the supply voltage change is asymmetrical. In the third case, VEE is shifted to 14 volts, but VCC is maintained at 15 volts. The average supply voltage is now 0.5 volts, and the common mode voltage with respect to ground is still 0 volts. This constitutes a change of 0.5 volts in the common mode voltage, which introduces a common mode error as well as a power supply rejection error. This slide summarizes the various PSRR definitions as well as general mathematical relationships. It is common to see PSRR represented in volts per volt, microvolts per volt, and in decibels. These equations allow you to make these translations. This slide shows the configuration used to simulate AC power supply rejection. Strictly speaking, inverse AC signal should be applied to both supplies such that the instantaneous average supply voltage is 0. This would keep the common mode voltage constant and no common mode rejection errors would be introduced. In fact, when performing an AC transfer characteristic for this configuration, the common mode errors are ignored by the simulator, whereas for a transient simulation, the common mode errors are included. From a practical perspective, however, the configuration shown is the most common way that AC PSRR is actually tested. Yes, it is true that this test configuration will include some common mode effects, but often they will be small compared to power supply rejection. Furthermore, from a practical perspective, looking at an AC signal applied to each separate supply is a more realistic usage case for the device. In this example, you can see that the simulated AC PSRR is very close to the characteristic curve from the datasheet. This slide shows how to use the post-processor Antenna Spice to generate the AC PSRR curve. Pressing the button circled in red will initiate the post-processor. The post-processor allows you to perform mathematics on curves generated by Tina Spice. The PSRR curve is generated by taking 1 divided by the offset voltage. From a Tina perspective, this is effectively the same as taking 20 log of the supply voltage change divided by the offset voltage change because the supply voltage is normalized and Tina automatically displays results in decibels. Here we are showing a transient response to an AC supply voltage. The AC supply voltage is at 1 kHz. The AC PSRR curve shows that PSRR is 80 dB at 1 kHz, which translates to 100 microvolts per volt. Multiplying the 2-volt peak-to-peak input signal by the 100 microvolt per volt PSRR specification yields a 200 microvolt peak-to-peak input offset voltage. The output can be calculated by multiplying the 200 microvolt peak-to-peak offset voltage by the gain of 2 volts per volt for a total output voltage of 400 microvolts peak-to-peak. It is important to remember that all Bode plots relate to sinusoidal waveforms. Later we will look at applying a non-sinusoidal signal to the supply. Let's take a closer look at the AC PSRR curve. The key point here is that the PSRR curve is a rejection and not a gain curve. You might look at the PSRR graph and think that it is a low-pass filter. In fact, if you draw the PSRR curve as a gain in microvolts per volt rather than a rejection in dB, you see that it is actually a high-pass filter. In other words, the offset error will increase for higher frequencies. The table illustrates this point for a 1-volt peak AC supply signal at 3 different frequencies. We can see that with increasing frequency, the PSRR in decibels decreases where the PSRR in microvolts per volt increases. Furthermore, the offset error introduced by the power supply signal increases at higher frequencies. Now let's look at how PSRR works when non-sinusoidal waveforms are applied to an op-amp power supply. In practical circuits, a switching power supply ripple can sometimes look like a triangular waveform. In the example shown here, we look at the effects of a 2-volt peak-to-peak triangle wave applied to the supply voltage of the OPA 132. Surprisingly, the output looks like a square wave with amplitude a little less than 10 millivolts peak-to-peak. What causes the shape of the waveform to change? Let's take a closer look. Before digging into the details, let's review the concept of a Fourier series. Any non-sinusoidal periodic waveform can be created with an infinite series of sinusoidal waveforms of different amplitude and frequency. So, for example, a triangle wave or square wave can be created by adding an infinite series of sinusoidal waveforms together. The example above shows how a triangle wave can be created by adding 5 different sinusoidal waveforms. The lowest frequency component is called the fundamental. The higher frequency components, called harmonics, are odd multiples of the fundamental frequency and also have smaller amplitudes. Notice that although we only have 5 harmonics and not a true infinite series, the resultant waveform is clearly a triangle shape. The mathematical Fourier series for a triangle waveform is shown here as well as the magnitude of the frequency spectrum. The theory behind a Fourier series will be helpful in understanding how the shape of non-sinusoidal waveforms is affected by different types of filters. This slide illustrates how a triangle waveform on an amplifier's power supply can be translated into a square waveform. Remember, the PSRR transfer function acts like a high-pass filter. Applying the Fourier spectrum for a triangle wave through a high-pass filter, the higher frequency components will be boosted. This has the effect of translating the triangle wave spectrum into a square wave spectrum. Another way of thinking about this is that the high-pass filter acts like a differentiator. When you differentiate a triangle waveform, it changes into a square wave. In this example, the triangle wave has translated into a square wave because of the high-pass filter transfer characteristics of the PSRR function. In other cases, the amplifier bandwidth limitations or slew rate limitations may add additional compounding factors that further distort the wave shape. The real point here is not that a triangle wave applied to the supply will translate into a square wave, but rather that the shape of the output waveform may be impacted by the PSRR transfer function as well as other factors. The Fourier spectrum for any periodic signal can be displayed using the Fourier analysis feature in Tina Spice. This can be useful if you want to see the harmonic content of your signals and how they are affected by the device transfer characteristic. This video discussed power supply rejection and how changing the power supply voltage on op-amps introduces a power supply rejection error. We discussed how to isolate power supply rejection errors from common mode errors and the effects of when non-sinusoidal waveforms are applied to an op-amp's power supply. Thank you for your time. Please try the quiz to check your understanding of this video's content.